Oh, well, this is the video assignment for signals and systems, and it's just a checklist. So the first step is make a recording of yourself, speak your name. So I've already did that before, and it's now saved inside the MATLAB, like where I opened the file. So it's record this as Vergel.m4a. So that just and to store that, I mean to play that part, I'm just gonna use the command IPFS and the audio read function will be able to play that uh, Vergel F4A. Then using the sound IPFS, I'll be able to hear what I recorded. So here we go.
My name is Vergel Jr. Pascual.
And for the second step, the variable fs is stored, so it's in here. It's 48,000. And for IP, to make it a single column, we just input the command IP, so IP, uh, this one, enter. Yep. So we're just gonna X on that and X on this. And for the next part is the plot the speech signal in the time domain against time in seconds and label axis. So for that, it's just we put the variable t and we got 0 to the length of the IP minus 1 and all of that by fs and, yep, and just plot the IP. Next is putting the labels in. So for that, we just go Y label. I'm gonna set it as the amplitude. Next one would be x-axis, so x label time in seconds. Yeah. So now just that. So next step is run the following code in MATLAB. So it's a code for the tone frequency. So we're just gonna copy paste this one. Just gonna make sure it's right. So for the values, we have the tone frequency of 2722, and for the noise cutoff is 20,717. Yeah, just gonna put it next there. So next is to synthesize high frequency noise and a tone. So for that, we're gonna use the NS. So the rand function will make that noise for us. And the size of that will be the same as IP. To create like the web as a high frequency noise, it's we're going to have make a filter. So I'm gonna use a butter function and a sixth order filter. And just the noise cutoff for us is to 20,717. So 17, all of that divided by fs over 2 to give us like a normalized frequency. And we're going to set it to a high pass filter. And filter then we're going to create a signal, which is all of those combined will be so IP plus NS plus tone. Actually, it's oh wait, tone here multiplied by pi multiplied by uh our tone frequency here is 2722. 2722 multiplied by e. Yep. Then we use the sig. All good. So now that's done. We're just gonna check this one. Next step is design a second order filter using MATLAB's butter function with a cutoff frequency equal to half cutoff noise. Okay, so to start, so another butter function, which is the according to instructions is second. It's a second order filter. Then our noise cutoff is 2077, but divided by 2, and of course all of that divided by fs over 2 for a normalized frequency. So I'm just going to put an X on that. So next is draw a signal flow diagram, write out the difference equation, and note the B and A coefficients of the system's design. So first we have to know the B and A coefficients in order to draw the signal flow diagram. So just to know the B and A coefficients, so for our B coefficients, just gonna it's your B and A. So those are all the coefficients. So for this, I'm just going to write them all uh, in a paint over here. So for B, so it's just gonna draw this. So as you can see here, there's gonna be two delays for both X and Y. Then the same goes for here. So this is going to be the first one. Then it's going to go to a delay. Not there. So these are delays. Yeah. So first X for B is 0.2327. 0.2327. Next is 0.4653. 0.4653. Then 0.2327. 0.2327. For the Y's, of course, 1, then negative 2.522. So it's actually going to turn positive once it goes over to the other side. So 0.2522. So, yeah. And since this is positive, it's going to turn negative. So 0.1828. 0.1828. Yep. So for this part, we're just going to write the equation for all of it. So for starting with, let's just change color to maybe, yeah. So y of n is equals to 0.2327 multiplied by x of n. So plus 0.4653 to the x of n minus 1 plus 0.2327 x to the n minus 2 plus for the y. Oh, actually, just so but here x n and y n plus there go to 0.2522 y to the n minus 1 because the y of n is already here. So next one is minus 0.1828 to the y of n minus 2. So that's going to be the equation. So I'm just gonna put here a check to draw a signal flow diagram. So next is we're going to calculate the first three outputs of the system if the combined signal is applied. So we're gonna MATLAB and just type sig. So this is gonna be our first three inputs. So 0.999. So our x of n will be equal to the following numbers. Well, actually, this is 0 here. 0.0949 and 0.0698. Just gonna So first one is easy. The y of 0. It's just going to be x of n, which is this multiplied by this number. So it's going to be 0.2327. So it's also here. So x of n, we're just gonna multiply that by x of 0, which will be 0.2327 multiplied by 0.0999. I'm just gonna pull up calculator here. So 0.2327. So that's 0.02324, 2325, 2325. Next multiplication is y of 1. It's going to be a long one. So it's going to be 0.02327 divided by x of plus 0.4653 multiplied by x of 0 plus, so we don't need this because it's not yet there, so that's just a 0. The same goes for y n minus 2 because we're just on the n minus 1, so 0.2522 multiplied by y of 0, which is this one. So this is going to be this number here. So that's 0.0949. Yeah, that's a 9. And this is going to be this value here, 0.0999. And then this is going to be this number, the 2325. So okay, so this is going to be quite long. So I'm just gonna pull a MATLAB on this one. Video split screen. Yeah. So it's gonna be 0.02327. Oh, wait, what? Yeah, 0.2327 multiplied by 0.0949 plus 0.4653 multiplied by 0.0999 plus 0.20. What does it have? that's right. 0.2325. So we got 0.1272. So this is going to be 0.1272. So for the next one, it's going to be y of 2. So 0.02327. Putting a 0 in there. It's 2327. So this is going to be x of 2 plus 0.4653. That's going to be x of 1. Then plus, yeah, now this kicks in the 0.2327 x of 0 plus 0.2522 uh, y of 1. Come on. Then minus uh, 0.1828 multiplied by y of 0. So this is going to be 0.0698. This is going to be this number here. This is going to be 0.0999. This is the previous answer, which is this one. So that's going to be 0.1272. And this is going to be the first answer. We got 0.0322325. So using MATLAB again, let's minimize this. And just going to start typing. So the first numbers are 0.2327. Let's put a 0 here. Multiplied by 0.06. Actually, it was not 0698 plus 0.4653 multiplied by 0.0949 plus 0.2327 multiplied by 0.9995 is correct. Yep. Plus 0.2522 multiplied by 0.172 plus the last one was minus 1828 multiplied by 0.02325. And hopefully it gives us the right answer. -42. What did I do wrong? Oh, oh. So 0.1115. Yeah, so to check that, I'm just gonna filter VA. Huh, that is not answer at all. Which part did I go wrong? Just gonna double check. Oh, I see. The first I actually got this part wrong. It's supposed to be zero. There's supposed to be a zero there. So that kind of cascaded it down. So I'm just gonna paste this, put a zero there. Yeah, so this is gonna be the second answer for that. And since that was wrong, this was gonna be wrong as well. Just gonna copy that one, paste it there. So this will be replacing this. There we go. So the first one we computed by calculator is 0.0232, and next is 0.744, which is this one, and the final answer is this, which is this, all pretty close. So as explained in the video tutorials, the slight difference is due to the rounding off, so that's pretty close. Just gonna put check on that one. Next is MATLAB filter function. Yep, yeah, we already did that as well. Next is design a minimum order filter which will reduce high frequency noise by at least 60 dB with a maximum of 3 dB ripple allowed passband. Okay, so for that, so the minimum order filter will be so it is the Butterworth function. So I'm just gonna put it as 0.5. And the just gonna set the noise cutoff, so 2717 divided by fs divided by 2 to get a normalized function. Oh, forgot. Forgot the so the parameters were 3 dB ripple and 6 one. So it's gonna be 3 decibels of free ripple and 60. Copy pasted the wrong. Yep. So so we have the N, which is what order filter that we were required. So fifth order filter, and we're gonna just frequency, then 0.5446. Then next step would be applying it to a filter. C and A. That's going to be butter option N and W. And we just solve. So that is this done. So next is to assign a second filter using MATLAB function to this is 40 dB. So we're gonna think it's gonna be a stop band filter that we're going to make. And since B and A is already used, we're gonna say B1 and A1. So not gonna be using a high order filter because apparently that causes things to go jaggy. So we're gonna stay at the lower order filter. So we're gonna use the fourth order filter. So in the cutoff frequency, so this is the tone frequency. So this minus 50 kind of gives it the range. So that's like the range, like 100 hertz range. So that makes it a stop band. Now to see if this is stable, we're going to use the C plane. Now, yeah, as we can see, it's stable because everything's within the circle. Yeah. So the poles and zeros are all within. So in order to check if that actual attenuates to of what's this 40 dB as requested. So we're just going to find the normalized frequency for 2722 because this is in hertz. So for that, just Fs over 2. So that's 0.1134. So using the freq z function. So as we can see, the frequencies are reduced. So at 0.1134, so 0.1134, so that's about here. So it's more than 40 dB. So let's say that's a success. So that is a success for that. So I'm just gonna put an X here. Next is apply both filters to the combined signal. The output of one filter is to be input in the other one. Plot the magnitude, frequency, content of the input and output hertz, label, axis. So we'll filter the signal. So y is equals to filter b a sig. So this is the for the first filter. The next one would be y1. So for this, we're going to use the output for this one, which is y. So it's going to be b1. Y1, 1. Then you got to use the max 0 to the length of IP minus 1 divided by the length of IP multiplied by Fs. And you just go plot facts out of the FFT of y1. Sequence. So you can see the signal here. Then I'm going to do hold. Then plot. So the signals has been attenuated over here. I don't know why the hold on doesn't work, but yeah, up here the noise has been reduced. It's not there anymore. And the speech itself is, yeah, the noise is attenuated so much. It's non-existent. Yeah, so it's just the hold on function not working. Next, just to label it. So, label my label should get set it to magnitude and X label will be set to frequency in Hertz. Yeah, check that in. Next is to identify a low frequency component that will produce a significant phase shift in the first filter, at least by over 4 radians, and pass a sinusoid of that frequency through the filter. Verify that the phase of the tone has been altered by the expected amount. Okay, so we're going to find the frequency response of that. So we're going to use freq_z. So we're going to find a spot, preferably a lower frequency, because lower frequencies provide a kind of a better resolution, because higher frequencies have kind of lower samples per cycle. So about -45. Yeah, about this much perhaps. Yeah, so maybe this spot. Yeah, so we're just gonna find which the x coordinate is 0.1718. So to find that in hertz, I'm just gonna double check there. 172. Yeah, I think I can use 0.172. So 0.172 multiplied by fs over 2. That's going to be 4,128 hertz. So using that, tone if you pass this tone into the previous system that we had, so y is equal to filter be a tone. So we're just gonna plot the tone. So this is the tone. So we're just gonna hold on to that one and plot y. Yep. And if we zoom on this one, yeah, there we go. So in this case, we should be getting a 45 degrees phase shift. So 45 degrees, so one waveform is about 360. So 360 divided by 45 is 8. So it has to be like an eighth of one one waveform must be like the advance of it. So if we just zoom in again, so this is about, yeah, this looks about right. So the phase has been altered by 40 degrees, 45 degrees. So I'm gonna put an X on that. So yeah, everything is complete. Thank you.